in this part of the induction motor, construction will be discussed. So how induction motor, construction part of the motor is going to be discussed in this part, how induction motors are constructed. So a stator, first part is a stator. So a three-phase winding is put in slots cut on the inner surface of the stationary part. You see here, this is the cut part. Here, this cut part is there. And in this slot, these are the windings. These are the windings placed in these slots. The ends of these windings can be connected in a star or delta. The end point of this three-phase winding can be connected either in a star or in delta. These windings are fed from three-phase AC supply and taken out, and these windings are fed from three-phase supply, AC supply, as shown here. These are the slots, and a stator, a stamping is here. These are the teeth, and here three-phase supply is given. So connections may be a star or maybe a delta. If it is in a star, it will look like this, and if it is in delta, it will look like this. So this is a stator construction. Rotor. So rotor, it can be either a squirrel cage. This squirrel cage is also known as brushless. So construction of the rotor is the squirrel cage winding consists of a bars embedded in the rotor slots and shorted at the both end by end ring. Here, this is these windings are shorted. This is end ring. End rings are given here, and it is being shorted by this end ring is placed here to make the winding shorted here. A squirrel cage winding consists of bars. These are the bars. Heavy bars are placed here. Suppose if induction motor goes on, takes a heavy current, then heating effect is also very less here, because this is not a wind, this is heavy bars are placed here. So it can take a high temperature also. So ends are and the ends are shorted through the rings. So in the case of the rotor, there is two type of rotor used for induction motor. One is a squirrel case that is also called brushless. The squirrel cage rotor is most common type because it is more rugged, more economical and simpler. Its advantage is that a squirrel cage rotor is the most common type because it is rugged, more economical and simpler. The reason is that if a high temperature rise goes on, then still it will not affect the bars of the conductors. So this rotor is called a squirrel cage brushless rotors. Rotor are basically two types for induction motor. One is called a squirrel cage, and another one is slip ring or wound rotor. The wound rotor has the same form as a stator. The windings are connected in a star. The terminal of the wound rotor are connected to three slip rings. These are the three slip rings. 1, 2, 3. This the wound rotor winding has same form as a stator winding. The windings are connected in a star. The terminals of the rotor windings are connected to three slip rings. Terminals of the windings are connected to the three slip ring, usually a stationary brush pressing against the slip ring. Here, a stationary brush are also placed pressing the slip rings. The rotor terminals can be connected to an external circuit. So the rotor terminal is connected to the external circuit. These are the some diagram that is shown here. This is the slip ring is presented here, and this is wound rotor. Wound rotor is also called slip ring, and this slip ring is here. Three slip rings are shown here. This is a shaft. This is a rotor winding is placed here, and ventilated holes are given here. Skewed rotor slots. Skew has some advantage that we will see later why these slots are put in the form of skew. Slightly twisted it is placed. So this is slip ring wound rotor. Two types of rotors are there. One is slip ring, another was a squirrel cage. A squirrel cage and slip ring rotors are there. Rotating magnetic field. This is very important part that is being discussed for all the working principle of induction motor. We need to understand what is rotating magnetic field. So this picture is taken from the source given here. You can visit also this link and you can see it's how the rotating magnetic fields are rotating, and its animation is shown on this diagram. You can visit this diagram also. This is very good video to understand the rotating magnetic field. Physical view is given here. So let us see here what is the meaning of rotating magnetic field. So just to understand the concept here, we can analyze this rotating magnetic field. So in the previous video, you can see how rotating magnetic field is running in the machine. So now we have to think about its. So for this case, we have to understand the concept of the rotating magnetic field. Here, three-phase AC supply is given. Three-phase AC supply is given. That current is shown here: IA, IB, and IC. So for different time of instant, the phase difference between these three currents will be 120 degree, and the plot is shown here. So how rotating magnetic field here? IA current is coming in phase A, IB is coming in phase B. Phase B is here, coming here, this position. Phase B is here, and phase C current is coming here, and it is taken out from this side of here. IA is coming here, A is here, and A S prime is here. Means one cross means ki inside the current, and dot means outside the current. So inside current and outside current. This is rotor. It has to rotate, and this is phase B. Positive or cross means current is going inside the page, and dot means current is coming outside the page. So that construction is being shown here, and the same thing is presented here. A dash, B dash, C dash is given here. So three currents are given here, and due to the flow of the current phase in A, the flux will flow. That flux is given by phi A, because if current can give a magnetic field in vicinity of it, which can be experienced. So that flux is shown here, phi A. For phase B, it is phi B, and for phase C, it will be phi C. These are the three flux given here, shown here. Now, the resultant of these two flux here, it is phi B and phi C, is shown on this axis resultant. So these two vectors, phi C and phi B, are shown here. Now, this flux for different time of interval, the flux value is changing with respect, because it is rotating. It is not stationary, so it is rotating. So in different time of interval, the value of flux is rotating, changing. Here resultant is along the C axis, that is B, and the angle between these two vectors are 120 degree. So its resultant will pass by this axis, and it will go through this axis. Same is given here. So now again here the diagram is shown as previous. It is here. So this is the rotating magnetic field. Ultimately, this resultant will go along this C axis. This also go in this axis, and finally the rotating magnetic field will look like this at different instant of time. It is shown here, it is rotating here, and this phi makes one revolution in t second. Flux, this resultant flux make one complete revolution in t second. This is called time period, and a speed of rotation equal to f per f revolution per second. This is called frequency also. And if had a p pole of machine, so n will be flux divided by p by rps. This is rotation per second. And if you convert it into rotation per minute, 60 we have to multiply. The 2 will be upside and multiplying by 60. So this speed will be 120 f by p, and this speed is also called synchronous speed. And the machine, a stator rotating magnetic field, will have to run at this speed, and this speed is called synchronous speed. Synchronous speed formula: one cycle is generated for one pole pair. One cycle is generated for one pole pair. One revolution generates one cycle for one pole pair. One revolution generates two cycles for two pole pair, and so on. One revolution generates p pole for p poles pair. Number of cycles per revolution equal to p. Number of revolution per second equal to n. And by doing so, the frequency of number of cycle per second, f equal to number of cycle per second. So number of cycles by revolution multiplied by revolution divided by number of cycles per second. This revolution is up and down, it is multiplied. So it is f equal to p multiplied by n, since n equal to n by 60 and p equal to p by 2 pole. This is per pole, number one half, two poles are, so p equal to p by 2. And after manipulation all these equations, we will get 120 f by p. I will give you another formula also. This can be very easily found out, that way I will give you later. So this is our rotating magnetic. When three phase balance current are applied to three phase winding A dash, as shown in previous slide, B dash, C dash, displaced from each other by 120 electrical degree in a space, a rotating magnetic field is produced, and that the speed at which the rotating magnetic flux rotates is called synchronous speed. This is the definition of synchronous speed, and its mathematical relation is 120 f by p, that is called synchronous speed. And if you convert into in omega, it will be 4 pi divided f by p. This is called angular synchronous speed. This speed is measured in rpm, rotation per minute. If we convert into the radian per second, then it will be equal to 4 pi. It can be very easily verified how we can get it. It is like this. This speed is, suppose this ns is this ns equal to 120 f by p. This is rpm, rotation per minute. So we know in one rotation how much angle is formed, 2 pi. So 2 pi angle is formed, and time taken is, suppose if it is t time to complete one rotation, so it angular speed omega will be equal to 2 pi by t, theta by t. So this omega will be equal to theta by t, and theta is 2 pi in one rotation divided by t, and 1 by t is nothing but it is the frequency. So this is 2 pi into f. And suppose we have this much of rotation, ns equal to 120 f by p, and this is called rotation per minute. So in one rotation, how much angle is formed? 2 pi angle is formed. So in ns rotation, how much angle will be formed? 2 pi into ns angle will be formed, and this is called rotation radian per minute. Now in one rotation, the angle formed will be 2 pi radian. So In ns rotation, angle form will be 2 pi into ns radian per minute. So we have to convert into minute into the second. So how much we will get? We will get 2 pi into ns. It is radian per minute. Radian per minute. So in converting in second, it will look like this. So it will be this is omega s equal to 2 pi into ns by 60. So now you put the value of this 2 pi, this ns value here, and we will get omega s this much. So doing just like this, we can do like this. Ws will be equal to 2 pi divided by 60 into ns is 120 f by p. 120 f by p. So we can convert it into, this will be 2 and 2 to 4, 2 to the 4 pi f by p. So it speed in radian per second will be 4 pi f by p, or in rotation per minute 120 f by p. Okay, so later we will see in another video and next topic.